This is Adam Shapiro and Taylor Welch presenting our heat transfer project on the transient heat loss of a cast iron skillet. Our goal was to determine whether or not the equations for transient heat transfer would accurately predict the amount of time it took for a cast iron skillet to cool off through free convection to a specific temperature.
Okay, so the method we used was a lumped capacitance method. This method just really breaks up the different types of heat transfer. There's the Q double prime right there. That's heat flux. There's heat generated. There's convection. There's radiation. That's what makes up the different parts of the lumped capacitance method. So what we did is, because there's obviously heat gradients in the skillet, we couldn't just treat it as one giant disk, but instead we chose to break it up into various disks. The measurements that we took, the temperature measurements, were taken from the middle of the disk, so we had to make a few different disks. So there's like a smaller disk in the middle, and then there's a few other disks outside that change with geometry and stuff. But so what we did is we broke it up into the disks, and then we did the lumped capacitance method for each one of those disks individually, and then solved for the middle disk, which was where we took our temperatures. We found the time it took for it to cool to 55 degrees Celsius. We put it in an oven at 160 degrees Celsius, and then to see where we were at, we compared it with an FEA model and the data gathered from that, and to see how good our test was.
So this is the skillet that we used. As you can see, it's not very large in millimeters. It's only 158.6, which is roughly about 6.5 inches. We found the density and all the other properties specific for cast iron. For the experiment, so there's a small correction. That it was placed into the oven at about 180 degrees Celsius, and the original plan was to begin timing it at 170 degrees Celsius. However, as soon as it was taken out of the oven, it cooled down so rapidly that it was almost impossible to get it set up at before it passed 170. So what happened was, as soon as we had a UV thermometer, laser thermometer, and I checked it every once in a while until it reached about 180, 190 degrees Celsius. And then I would attach a wire to it, pull it out of the oven, and wrap it and hang it from a cupboard so that it was suspended in air, a good distance away from any other surrounding objects. And then I would begin timing it as soon as it reached 160 degrees Celsius. And we would write down the amount of time that passed after every 5th degree that it cooled down.
So it was a lot like the lab we did, and it was pretty much the same thing. Just every 5 degrees we took a measurement to see how long it took in between those 5 degrees.
Exactly.
So here's the properties of air. I just wrote them down here just so we could see at a couple of different temperatures. Because the rings, each ring was at different temperatures, the outer ring obviously cooled the fastest, the inner ring cooled the slowest. Our T-film for our properties changed kind of throughout the whole, throughout the experiment in different parts of the skillet. So I put 360K, 340, 320, 300, just because these are properties that we used, just to make sure that we changed our properties as the skillet cooled. So here's the rho is density, then we have the viscosities, we have the alpha, PR, and K, or the Prandtl number and then K. And then here's where we calculate our free convection coefficient. The Rayleigh number, gravity, B was 1 over our T film, and then our T surface minus our T infinity times the length cubed. This Rayleigh number was for a vertical plate because we suspended it vertically, so the length ended up being the diameter. That calculated our Rayleigh number. We used the vertical plate Nusselt number correlation, and then from there we multiplied it by K over L to get our H. And our H, you can see the mathematical file that we have, it came out to be about 6.5. So dividing up the skillet, here's kind of the equation that we used. There was no heat flux or heat generated. So it really came down to convection and radiation. And if you remember, Brother Daines talked about how if you have both terms, you have to use one of those, a numerical solver, which we did use. But anyways, here's kind of how it is. The outer ring, the red, shows radiation going out and convection going out. Then you have the inner ring, which is radiation and convection going out, and then the innermost one with radiation and convection going out. Here's the numerical solver, just really quick. You can see the three rings at the top. There's three different equations that are all solved, and then I plotted all three of them right here down at the bottom. The line at the top is the innermost one. That's the one that cooled the slowest. And you can see that it, according to this, it took about 622 seconds. And that's how long it took with radiation and convection leaving. So there's just our calculations.
We did an FEA model as well to compare the results from the numerical methods as well to the collected data. And it turned out that the FEA model, we used a convection coefficient of 8, which was a little higher than the calculated convection coefficient. And that can be, that could be the result of the slight error that we have. It turned out that the FEA model cooled off a little bit quicker and to a lower temperature than the collected data did. And in order to simplify the model, it's important when we do FEA models to simplify as much as possible. And when I had the handle modeled with the rest of the skillet, it was creating temperature gradients up into the handle, which was throwing our data off. And so in order to, we eliminated the handle and just had a disc in the same geometry as the main section of the skillet, and it turned out to be a lot more accurate that way.
Okay, so now we're just trying to figure out why it was wrong, because if you saw that the FEA had it cooling off at about 1,200 seconds, and it actually took us about that much time. So the FEA and the experiment matched, but our calculations didn't, and this is probably why. In between the rings, obviously, if you were to have those rings, they'd be touching and there'd be conduction. So if we account for the conduction, that would change it. Anyways, that's kind of right here in conclusion. Our FEA was accurate, so the convection coefficient that we calculated was accurate, but obviously we need to account for conduction and a few other small errors in order to make our calculations fully correct. Thank you.
Thank you.